I posted this Google Drive link in the chat. I will later post several times in case new people are joining. And here the two main documents is this agenda, which I will show. We'll follow that, and another one is this hands-on exercise. So the agenda, the full agenda, very detailed agenda, is here, and the exercise sheet is here. Okay. And also, when we started doing the software, I will show you the on the two GPU machine. One is the Satan, one is the Instinct. This is the two nodes at the University of Oregon. One with NVIDIA, one with AMD. I will show you the this CMaker configure script. And I'll show you how you can modify. Actually, you can, hopefully today, if you are adventurous, you can even install this on your own machine. Okay, so let's get started. Before we get started, are there any questions we can feed? Any logistics? We have plenty of time today, so we don't need to rush. All right, no, then I will make this full screen. We'll get started. Let's see, it's slideshow right here. Okay. All right, so this tutorial is about sparse direct solver and direct solver based kind of preconditioner. And the first half an hour will give a very high level overview of the software packages, SuperLU, STRUMPACK, Butterfly Pack. And this is will stay at the higher level at this point. And then the next session is from 10:30 to 11. We're hoping to get everyone set up for the exercise session. So this half an hour is mainly to work with the software to get software set up, and we'll start doing some examples there. But most of the examples, detailed examples, we'll do that in the session here. There's 11:40. There's a session, and then 12:10 is a bigger block, the session about exercise about STRUMPACK. And then in between the sessions, there are two breaks. Also, let me see what else I want to say here. Okay, so this half an hour is mainly about the tour about sparse direct solvers. So it's dive a little bit of detail into the global landscape of how people do, what are the algorithm components there. And then I'll talk a little bit about more specific for SuperLU. And then Peter will talk about more specific about STRUMPACK. And STRUMPACK has a lot more functionality, so we want to spend a little more time on that. And the hands-on instructions is in this folder. All right, so with this agenda, since it's a long tutorial, long session, so but at least what's going on every half an hour. So if you need to deal with something else, you feel free to go off. All right, so I'll start with overview of SuperLU. It's actually a suite, so there are, and the name comes from the algorithm. It's supernodal sparse LU, so it's a super LU. Okay, it's not a regular LU. Okay, but anyway, so the web page is here, and so from this web page you will see a lot of papers. A code is pointing to 3 codes, the GitHub, and it's actually 3 separate codes. So it's when you say SuperLU, it's a little bit vague. It started serial and then gradually moved to shared memory in those days, and then become distributed memory. And I want to just highlight the differences between these 3 libraries. So the serial and shared memory, it's relatively easy to implement. I would say relatively easy. So it's never easy for sparse direct solver, but relatively. So we can actually do partial pivoting. And I will show you in the algorithm session that what's the difference between this partial pivoting. Numerically, this is more robust, but in order to favor distributed memory, strong scalability, we sacrifice a little bit the numerical property. Here we're using static pivoting, which is a little bit less stable than this one. But in practice, it works really well. So it's surprisingly well, actually. And then in terms of language, we started this a lot earlier. So it's a C-based. Actually, it's not Fortran-based. It's already pretty good. It's difficult to do sparse code in Fortran. But then with the shared memory, we first added the P threads. And in those days, OpenMP was not a thing. And then later ported to OpenMP. And then distributed, we added the MPI, of course, and recent several years started adding CUDA and heap. And the Intel one is still in progress. It's not ready for people to use that. And the data type, it's all different data types, so you can mix actually. The input format from the user point of view, it's very simple, but internally it's a lot more complex in order to get the performance. So the user input is just compressed row, compressed column. And in the distributed case, it's distributed compressed row. So a few high-level points I want to emphasize is numerically, the MT version and serial, they are very good, numerically the same, and usage is the same. You just the same number of OpenMP threads. And in fact, nowadays, if you look at a download, maybe more than half of the downloads are still in sequential code. The reason is it's very robust, and whenever users, people, our collaborators, they have difficulty numerically, I always go back to sequential code to do some numerical investigation. So it's still very, very highly used, very reliable. And the serial code, distributed code, you can link together. So that's convenient for a lot of applications. And all precisions, the 4 precisions that you can link together. We have photo interfaces and available from many other high-level libraries and the high-level packages. These are mostly done by the other people, so we're grateful to them. And then this is the capabilities in the bulletin form. So the sparse direct solver is the main part is you factor into LU, and then this is lower triangular, upper triangular, and then you do the lower triangular solve, upper triangular solve. But there are a lot of subtleties, whether the matrix is non-symmetric pattern, symmetric pattern, symmetric numerically, etc. So there are a lot of different codes which you will see later. And then in the sequential code, we have this very good incomplete LU with threshold and partial pivoting. So it's a numerically very good preconditioner, but that's not scalable in the distributed case. That's why later we started working more on STRUMPACK type of technique to do, you can consider that to be approximate factorization as a preconditioner. And the big deal here is sparsity preserved ordering. And we provide a lot of options. And then there's user controllable pivoting. I mentioned this partial pivoting, static pivoting. This is mainly to trade off sparsity, amount of field, parallelism, and scalability. And in the sequential code, as I mentioned, it's very robust. Oops, with partial pivoting, so we can do a lot more analysis. Numerically, you can do condition estimation, very reliable, and then you can analyze the component-wise error bounds, etc. So the early system, we did the CUDA heap that today we're going to show, and in progress is Intel. And this is just some parallel scalability highlights over the years. So we published some papers trying to improve the strong scaling. And the triangular solve particularly is very hard. we made this last 2-3 years, we made very good progress in terms of strong scaling. But the code, we're still in the prototype stage, so we're not going to show today. So here, I just want to give you a sense of the development history, and then you can see that for even for a simple say sparse direct solver, it's used, but its development actually takes a long time to get many pieces in place. So the work was started when I was a PhD student at Berkeley. So I chose this topic area to be my thesis. And at that time, the big thing in computer architecture is the deep memory hierarchy and the symmetric multi-processor, which you share the memory, and then the different process, different core, at that time they don't call it's not core, different processors, CPU. Then you have a big cache, but usually they have a cache coherent protocol to maintain, which causes a lot of memory traffic. And then to a lot of numerical algorithms, you need to think about locality, increase arithmetic intensity. So that's a lot of work was done during my thesis. The first release was, serial was, I don't know how long, ages ago. And then first release of shared memory code. And at that time was funded both by SF as DOE. And then after I started working at LBL, obviously the big demand is distributed memory code. And the design is actually very different from the shared memory code. So we started, algorithm-wise, started from scratch. So that's did a lot of work with distributed memory. And the funding level for these 10, 15, let's say 15 years is actually not very high. It's about equivalent to half a FTE. So it's a fraction of me, and from time to time we have students, summer visitors, etc. So contributing. And then starting ECP is really good. What is good is about we have concentrated the funding level. So it's equivalent to about 1 FTE with multiple people. We can focus the work on a lot more in terms of algorithm innovation. So here the two things which I will show in detail in the algorithm is one is obviously we spent a lot of effort trying to do GPU, since the exascale machines will be GPU based. Another one is pushing the envelope of strong scaling, so which we developed this 3D communication avoiding algorithm, which I will show in the algorithm session. So this actually taking a lot of effort. It's not a fraction of a certain person can do this very efficiently. So this shows how much time did that go? 11 minutes. Okay, I want to finish actually. So I will show you roughly this in terms of two algorithm innovation, GPU and the communication avoiding. Oops. What's the effect in terms of speed? So we start a baseline in the distributed code is a 2D distribution, which you will see. And then after we added the GPU, just a gem load, offload, but gem is very sparse, very small in the sparse code. So you get something, reasonable speed up. And then from baseline, you go down here to communication avoiding, you can get a lot more speed up on large scale machines. And then added on top of this, you added GPU, you get some benefit. But in this case, we also added more of loading stuff, not only gem, but also scatter operation in the short complement update. So you get a little more benefit. And in terms of triangular solve, the baseline is also 2D algorithm. And then you do communication avoiding, you get a lot more strong scaling. And adding GPU, it's a very hard problem. And we managed, so for example, a couple of years ago, one Summit GPU, we can get over 8 times the speed up over the cool sparse. And then we use one-sided communication. to hide you, basically to speed up, overlap the communication among different MPI processes and the CPU, you get some speed up also. And the software dependency is actually for SuperLU is pretty minimum if you consider a sparse direct solver. So if you don't have anything, for example, you actually don't need any external, everything is internal. So when you do the CMake, you can say, I enable internal blocks. I enable this internal blocks, will use internal blocks. And I will say enable parameters to be taken, this to be off. So that means we'll use internally the default we have for good minimum degree ordering. But of course, this is not the highest performance. So we highly recommend blocks and parameters and Scotch, in fact. So I didn't list the Scotch here. It's mainly because we're using the same parameters interface to access Scotch. So you just need to swap the linking of the two libraries, you get two different algorithms. And if you want even more performance, there are some other features. So we use, of course, GPU and then the LAPACK combinatorial class. So those are the software stack. So I will stop share. If you have any quick questions, then we move to STRUMPACK overview. No quick questions, so we can stop. Peter can start.
Hi, can everybody hear me? Okay, so I will go ahead and give a brief overview of STRUMPACK, which stands for a structured matrix package. It's a sparse direct solver, and it also provides several rank structured preconditioners. So the sparse solver in STRUMPACK is fully algebraic. It's a sparse direct solver, and it then also provides several approximate sparse factorization preconditioners. So this is somewhat similar to the idea of ILU, where you have L and U factors, which are not exact but approximate. But instead of dropping elements from the LU factors, we will approximate the L and U factors using rank structured approximations. So we will try to find dense blocks inside the sparse LU factors and then approximate those smaller dense blocks using low rank approximations. I will go through the details of the algorithms in the later part of the tutorial. And so STRUMPACK is based on the multifrontal LU algorithm, which is somewhat different than how SuperLU does this, but we will also discuss this difference later. And so these rank structured approximations we apply to dense subblocks in the sparse LU factors. We can also apply them directly to dense matrices from various applications. For instance, large dense programs you get from discretization using boundary element methods or structured matrices like Cauchy or Toeplitz problems or like kernel matrices or covariance matrices, things like that. So we have several of these rank structured matrix representations in STRUMPACK. The first we started with is the HSS format, which stands for hierarchically semi-separable. There you hierarchically partition the matrix into block 2 by 2 structure, and you approximate the off-diagonal blocks using low rank. Then we have another format. This is called the block low rank format. There you don't hierarchically partition, but you just partition the matrix in a grid of smaller blocks, or also called tiles sometimes, and you approximate those using low rank. And then we have inside STRUMPACK also integration of butterfly pack, which is being developed by Yang Liu, also in the Scalable Solvers group at Berkeley. And butterfly pack implements a so-called butterfly matrix decomposition, which you can think of as a algebraic equivalent of inspired by the fast Fourier transform. So this is targeting high frequency problems. So we can use this inside the STRUMPACK sparse solver to precondition, for instance, high-frequency Helmholtz or Maxwell problems, which are otherwise very hard to precondition or to compress with other rank structured formats. And then you also can use the hierarchically off-diagonal low-rank format, which is implemented inside Butterfly Pack. This is somewhat similar to the HSS format. And then there's also hierarchically off-diagonal Butterfly Pack, Butterfly, so that replaces the low-rank part with Butterfly. And I'll discuss this more in detail later on. We also have integration of the CFP package, which provides compression for floating point data, 1D or 2D or 3D data. You can use that to compress a regular dense matrix, but then of course you cannot do computations on this compressed matrix, so this does not save us any computation, this compression, but it allows us to solve larger sparse problems, for instance, because we can use this lossy or lossless floating point compression to compress the L and U factors of the sparse solver. So here's a link to the STRUMPACK website where the development is done on GitHub, and we also have a separate website. So this GitHub repository has the latest development branch. You can file issues there. We post our releases there. And this other website, which you can also reach from our README in the GitHub page, has the manual, which we created through Doxygen, and it also has the other Doxygen documentation of the interfaces in STRUMPACK. And we also post related publications there. And these are the current developers of STRUMPACK. So STRUMPACK is written in C++. It has templated interfaces for the 4 different standard precisions, a single and double precision, and a single and double complex precision. And typically you can specify these 2 template parameters. One is the scalar precision, and the other is the integer size. So this can be 32 or 64-bit integer, but they have to be signed. So these are the integers that will be used, for instance, to specify a sparse matrix in the compressed sparse row format. And it's released using the BSD license. For parallelism, we have OpenMP threading, MPI distributed memory parallelism, and now also the GPU capability through CUDA for NVIDIA, HIP and ROCm for AMD, and SYCL or DPC++ for Intel GPUs. We originally started with the OpenMP code and spent a lot of effort trying to get that to work well using OpenMP tasking. This really helped us to exploit the multiple levels of parallelism in the code, because we have the algorithms in STRUMPACK are quite complicated, and we have sometimes up to 3 levels of nested parallelism in the algorithms. And by recursively spanning tasks within tasks, we get good scalability within a node using OpenMP. And the dependencies are BLAS, crucial for performance, and then LAPACK and METIS. So METIS is used to do the reordering of the sparse input matrix. And MPI is optional, but if you enable MPI, then we also need ScalaPack. If you have MPI, then you can use PARMETIS, which is the parallel version of METIS, or PT-Scotch, which is the parallel version of Scotch. So this Scotch is can also be used to reorder the matrix. And then for GPU, you need QBLAS, QSolver, or HIP plus HIP solver on AMD. And then the SYCL or DPC++ code uses the one API to do BLAS or LAPACK operations on the Intel GPU. We can also use Slate. Slate is a modern replacement for ScalaPack, which provides also a GPU offloading capability for ScalaPack-like operations. I mentioned the CFP, which is a library for compression of floating point data, and then Butterfly Pack. And finally, another dependency is the combinatorial BLAS, which we can also use for static pivoting. I'll come back to that later. So for this GPU support in STRUMPACK, so we have support for NVIDIA, AMD, and Intel GPUs. Today we will be demonstrating the NVIDIA and the AMD support. But this GPU support is for now only in the Sparse direct solver. We have not released any GPU support for the preconditioners, so we don't have released support for the rank structured formats. But that should be coming soon. And also, our GPU-enabled code has the same interface as the CPU code. So the interface takes as input the matrix and vector, the right-hand side vector, from CPU memory and returns it also in CPU memory. A fully GPU interface where the matrix is on the GPU will be added later. The reason why we don't have this yet is because inside the code we have these several phases that still need to be done on the CPU at the moment, like ordering of the input matrix using these external dependencies like Metis and Scotch and redistribution of input and output vectors. And so, as I said, we're working on GPU support for block low rank. And also we have a postdoc working on GPU implementation of H and H2 matrix compression. So here's just a quick teaser for the GPU performance in STRUMPACK, where we solve a sparse linear system with a matrix coming from a discretization using finite elements on a 3D mesh with a simple 7-point stencil, and we scale the problem size from 20 cube mesh to 200 cube mesh and run this on a single GPU. For instance, a V100 from Summit or an MI60, MI100 AMD GPU, or a more standard like a gaming NVIDIA RTX 2060. You can see here that the performance goes up to about 7 teraflop using single precision on the V100. So that's about 40% of the peak performance on this V100, which is not bad, I think. And then the difference with single precision and double precision is typically a factor 2, except for this RTX 2060, where the difference is much larger, because that doesn't really have hardware support for double precision. And then this is just one slide to illustrate the capabilities of the preconditioners in STRUMPACK. So we solve this viscoacoustic wave propagation problem described by this Helmholtz equation using, so we solve this on a regular 3D mesh. And here on the x-axis, you see the mesh size ranging from 150 cubed all the way up to 500 cube. And if we solve this using an exact sparse solver, that's the blue line, that's just no compression. So you have the exact L and U factors of the input matrix. This would scale as n squared, where n is the total number of mesh points, so k cubed. So that would become infeasible for these large problem sizes, especially when you look at the memory requirements. The memory here scales as n to the power 1.5, I think. But by then applying compression to the sparse L and U factors, we can drastically reduce this memory requirement and also asymptotically reduce it to linear scaling of the memory. So the green line here uses a combination of both block low rank and hierarchically off-diagonal butterfly compression. And the orange line is a combination of HOTBF, BLR, and the ZFP compression to even further reduce the memory requirements. Similarly, for the scaling of the factorization time, we get close to linear or log linear scaling for the time compared to n squared scaling of the time for the exact sparse solver. So then, yeah, okay. But so these previous results were using butterfly pack to implement this HOTBF hierarchy of diagonal butterfly decomposition. So butterfly pack is a package with solvers mainly for dense matrices, So it implements this butterfly decomposition, which I will explain more later. It also has this hierarchically off-diagonal low rank structured format, and HODBF with butterfly instead of low rank. It also has some support for the more general hierarchical matrix format, but we haven't really explored the use of that inside the STRUMPACK sparse solver and preconditioner. And butterfly relies a lot on randomization. For instance, to construct a butterfly or an HODBF representation of a very large dense input matrix, it's typically not necessary to first construct your entire dense input matrix, but it's enough to specify a matrix vector routine to butterfly pack, and butterfly pack uses that then in combination with a randomized scheme to efficiently construct a butterfly or HODBF representation. Another way to construct such a representation is by providing a routine which can evaluate individual elements of the matrix. For instance, you provide a routine that can evaluate entry I, j of the matrix. Or for performance, it's typically better if you can write a routine that evaluates multiple entries in a submatrix at the same time. So this can drastically reduce communication. So, and then when the butterfly matrix or the HODBF matrix is constructed, the butterfly pack can use that to do efficient matrix vector multiplication or factorization of an HODBF or HODLR matrix, and then solve linear systems. Butterfly pack is written in Fortran, in modern Fortran, uses MPI and OpenMP. You can easily find this on Google if you Google butterfly pack. It's also developed on GitHub with a BSD license. So I think now then we will move on to preparation for the hands-on session. Let me first check.
Peter, maybe I will talk a little bit about the CMake stuff.
Okay. Yeah.
So, and probably 5 minutes. And then we'll get people can start doing stuff. So the first thing I want to ask everyone is if you want to do the hands-on today, we are using this Frank system at University of Oregon. Can you put, just tell us in the chat, so I'll show you what we're trying to do. That's the correct screen, right?
Yes.
Yeah. So in this document, this hands-on exercise document, there's a lot of instructions here. And what we're trying to do is to assign each person to one account. So this is the machine at University of Oregon, and they graciously provided the 20 accounts for us for today. Hopefully that's enough, but if it's not enough, it's actually better. You can try to install on your own machine. And what I did here is I assigned the people that I got email. We received the emails. They say they are going to use come to the tutorial, do the hands-on. So these are assigned. How it works is you log on to the machine with the login name, for example, student01. The password is this. And then Alan, if he wants to use this, you will be using this account. So everybody has a unique account. Of course, everyone knows the password of everybody else, but try not to do any malicious things. So we're trying to do this assignment. If let me see whether people have started. Since I see there are a lot more attendance than the 20 accounts, so we cannot assign everyone. That's why in the chat I'm asking people if you want to do the hands-on, please put in the chat. We'll just assign you to account. All right, so let me see. So Yang, I see Bryce has in the chat. Yang, can you help do the assignment?
Yes, I'll do
okay, thank you. And I will continue to you. Hopefully you're all seeing my screen, okay? So let me see, do I start from the correct place? Yes, okay. So the plan is for next 30 minutes, we're actually slightly behind, but that's okay. And what I want to show you is the, we have two options for this hands-on. They are both easy to use. But I want to show you, take a few minutes to show you how the CMake works. So the installation, for convenience, we have pre-installed everything for the tutorial. In theory, you don't need to do any in terms of installation. So for CMake pre-install on the machine, in the hands-on document there are instructions on how to log on the machine. So once you log on to the machine, you will see the directory here, go to that directory. And then in this Google folder, there are two simple CMake scripts I want to show you so you know how this works even on your own machine. One of them, Satan, the machine is a NVIDIA machine. The Instinct is the AMD-based machine. Okay, so let's go to this window. Can people see the fonts? Okay, the size?
Yes.
Okay, that's good. Okay, so I logged on to this authors, this machine. It's the front-end server. Okay, and right now I'm in the home, and then I will go to the this directory. The color is difficult to see, so I'm going to this tutorial directory, and then you can see that in this directory there are two subdirectories. The reason there are two different machines we're going to work with, so we don't want to mess up. So let's go to the Instinct. This is the AMD machine, okay? And then you go to another directory, which is manual install, okay? So here, what I want to show you is the one CMake script. It's difficult to see, where is that? There, okay. So I named this file called Instinct configure SuperLU.sh, which you can download from the Google Drive. And then on this machine, we need to set up the environment variable, some system software. So it's convenient that they already have everything packaged in module. So you can just say module load these things. And then you define the compiler, using for parallel code, we use MPI, CC, MPI, C++, and MPI F90, okay? This is for the Fortran interface, but in practice, by default, you don't need Fortran. And so this is the link type. And then the BLAS library, we use this open BLAS, okay? This is something you will define on your machine. So then we'll see the next several blocks of code, how to get the external dependency. So for example, if you want to use parameters, then you will say, define these several variables, the parameters directory, and include the file directory, the meters directory, and then the library directory. And then in the CMake, you will see enable, this is for heap, so we'll use enable heap to be true, okay? So these are the definition. And this block here is to get the parameters. So you can say a wget from their website. This W means the web get, right? And then you tar to do this sequence and copy into the, so this is make configure, that's the main installation, the compiler command for parameters. And then you do a make install, then it will be installed in the directory that you specified earlier. So copy the include header file into the include directory. So that's this parameters. Similarly, and in this exercise, we're using OpenBLAS. So you can say it's Git based. So you say Git clone from OpenBLAS and then define this, their make is using this, I think it's CMake based, but it looks like a regular, configuration, regular make. So that's this OpenBLAS. And the next block is SuperLU. You can get, it's Git based. You say Git clone, and then a number of these lines. So the CMake, once you get those set up, the CMake is just with these flags. And some of these, they are optional. You don't need to do the system will, CMake will find it. But the several things I want to mention, one is since we're using heap, so you will say define heap CC flags. This is some flags we want to use for this machine. And you say enable heap lib, which uses this define the enable heap lib. It's actually just true here in this case. And the other thing I want to mention here, I think that's it. So the, and then here define the parameters include the directory, define the library. So that's the external library. Are there any questions about the CMake structure? And in theory, you can just modify this script to work on your machine to make sure you, if you want to use a heap, then you will say, where is the heap library? So it's just these two lines, enable heap lib and install heap CC flag. So you can use on your, do your own machine. If you don't have a heap, you just want to do a CPU install, you just say enable heap lib to be false. That's it. So you get a CPU version. All right. So then if you look at my directory, so there will be OpenBLAS is installed here. Parameters is installed here. This is coming from that script. And then SuperLU dist is installed there. And then we have the whole configure.sh, which installs the STRUMPACK and also butterfly pack. So the whole script takes probably 10 to 15 minutes, but the SuperLU, this simpler script takes about 4 minutes. So that's what I want to show you about CMake, and then Peter can lead the discussion about this singularity image. All right, Peter, I will stop.
Okay, so we have actually, these two different options for the hands-on. One is what Sherry was just showing. You log into the machine and you run these scripts in your home directory. Or we have a prepackaged singularity image, which is like a container image based on a Docker image. I will now go through this. So the instructions are at this link. Here it says use the Slack channel to get an account. So just go through to this Google Drive and then go to the hands-on exercises page. That takes you here, and then scroll to the bottom so you can get an account here. And I think Yang is helping people with that. So then once you have this account, you can SSH to the machine Ortus at U Oregon. But here you put your student and then your number, enter the password, and then for NVIDIA we're using this Saturn, so just SSH Saturn, and also we'll use this ECP folder in the home directory, and then go inside the subfolder Saturn there. And now, because we are on Saturn, which has an NVIDIA GPU, we will launch the Singularity image using the --NV to request access to the NVIDIA GPUs. So copying this line. By the way, these slides are also in this Google Drive, but the instructions on how to do all of this are also in this hands-on document. But so now I will launch this Singularity image. So this Singularity image contains an installation of the entire E4S software stack, which is installed using SPAC package manager. But then we still have to load the individual packages. So now I'm going to load SuperLU dist. So you just say SPAC load SuperLU dist, but there are multiple versions of SuperLU dist installed. So we have to specify the developed version. And there are also multiple installations of SuperLU dist at develop. There is one for CUDA and one for HIP, ROCm. So we have to specify the correct one. Sorry, just to show you that there are multiple, but so you can select the correct one by specifying plus CUDA and the specific CUDA architecture. So this was compiled using the CUDA architecture 80, because here we have I think an NVIDIA A100 on Saturn. And once this is loaded, we can check the install location for SuperLU dist. And that returns you the folder where it's installed, and then you can go into that directory and then in the lib example subdirectory. And this is where the examples for SuperLU dist are installed. And then you can just check if everything is working correctly by running a small example. So first we set the number of OpenMP threads to 1. You can experiment with this. But please realize that this Saturn, there's only one machine with one GPU. So all attendees of this tutorial are using the same machine, the same NVIDIA GPU. So that could impact the performance if you're running some larger problems. So this all seems to work. It finds the A100 GPU. The residual here is machine precision. So that's working correctly. And then you can do similar things. You can disable GPU offloading by setting this SuperLU accelerator offload to 0. We will go through these steps in more detail later. And then here are the similar steps, but for AMD. So instead of SSH to Saturn, you SSH to Instinct. So you'll have to exit Saturn and go to Instinct. Then you can do the similar steps. You use the Instinct subfolder, and when you launch the Singularity image, you specify --ROCm instead of NV, so that you have access to the AMD GPU. And then when you load SuperLU dist at develop, now you say I want to use the ROCm variant instead of the CUDA variant. And this was compiled for the GFX 908. Again, go to this subdirectory where the examples are, and you can test this out. Let me check the chat quickly. Okay. And then we have similar instructions for the STRUMPACK examples. Let me do this on Saturn for NVIDIA. I'll again launch the singularity image. So the STRUMPACK examples are in a folder inside the singularity image called Sparse STRUMPACK examples. But because the singularity image itself is read-only, you cannot write in there. We'll copy these examples into your home folder, because the singularity actually mounts your home folder, so you can access that. So when you copy to this dot, I'm assuming that you're inside this ECP tutorial Saturn folder, yeah, which is correct here. So I've copied these this example folder here. Let me now go into that folder. So in this folder, there's a couple of examples. You see the CTP files, test mm double, test HODLR, test mm double, MPI dist, and so on. There's also one Fortran example and one C example. And there's a simple CMake lists file, which you can use to build these examples. And this also illustrates how to use STRUMPACK through CMake. So basically, you just do a find package STRUMPACK, and then that should also load all the dependencies that STRUMPACK was built with, except for HIP. We had to still manually load these. But then you still need to do a SPAC load of CMake and SPAC load of STRUMPACK itself. So now this is loaded. CMake should find STRUMPACK. We're trying to build it. So we have a simple build script. We have two different, one for CUDA and one for HIP. So this just makes a build directory and runs CMake in that build directory using this CMake list file I just showed you. So we can build all the examples. This will take less than a minute or so. And then the examples will be in the build directory. Let's just test if this is working. Right, so we have a relative error, close to machine precision. It's doing some iterative refinement and so on. So this is working. We're going through these details more in a later part of the tutorial. And then you can do the same also with the singularity image, but then on Instinct, if you want to run on an AMD GPU. Again, just specify a ROCm instead of NV. The other steps are the same, except when loading STRUMPACK. And then this is what Sherry explained. You can just log into the account, go through this to this folder, Saturn or Instinct, and then the subfolder manual install. So that's where this where we have this config and run script. If you config will build all of these packages, SuperLU, dist with the dependencies, parameters, OpenBlast, and so on, and then also build ButterflyPack and STRUMPACK. And there are some examples in this run script. You can open this, look at the examples. One thing I forgot to mention, if you want to look at the examples for the SuperLU dist, at the source code for SuperLU dist examples, you can do. Those are installed here at the Sparse SuperLU example folder. So for instance, here these .c files, or you can also just go through them in the manual install folder in SuperLU example folder. Are there any questions about this hands-on? Are people able to log into the machine? Okay, so in the slides here, I also have some more information about how to manually install STRUMPACK, or the different options to install STRUMPACK. I'm not going to go through all the details of how to run CMake for STRUMPACK, but these slides are more also for reference. So there are a lot of slides on how to run CMake for STRUMPACK, but you can also use SPAC to install STRUMPACK. STRUMPACK and SuperLU dist and Butterfly Pack are also part of the XSDK software stack, so you can also install XSDK using SPAC, and that will install all the 3 packages: SuperLU dist, STRUMPACK, Butterfly Pack. We're also part of E4S, so the container we're running is based on a container from the E4S package. There's also an interface from PETSc to STRUMPACK and from PETSc also to SuperLU dist. So you can also install PETSc, and when you're running configure on PETSc, you can specify download STRUMPACK or download SuperLU dist with some more options. But then that will download and configure and build STRUMPACK for you. So the STRUMPACK CMake installation is pretty standard. You git clone, and then you make a build directory on CMake in there. You can enable or disable MPI and OpenMP and so on. To enable GPU acceleration through CMake, you specify STRUMPACK use Cura equals on, or use HIP is on. One of the 2 should be enabled, but not both. You have to pick one. You can also build for SQL. There's another slide about that later on. And to get STRUMPACK working properly on GPU, you should also enable Slate if you want to run on multiple GPUs using MPI. So Slate is a scale-up pack replacement that provides GPU acceleration. And Slate is built on top of BLAS++ and LAPACK++, so you have to specify where that's installed, so STRUMPACK CMake can find that. This is how you enable SQL or DPC++ support. STRUMPACK use SQL is on, and then you specify this DPC++ compiler and the corresponding Intel C and Fortran compilers. For now, this is only single GPU because we cannot yet run Slate on multiple GPUs using SQL. This is how you specify the compilers, which is standard CMake. You can manually specify where your BLAS libraries are and LAPACK libraries, or you can specify the BLAS vendor. We also have some experimental support for 64-bit BLAS and LAPACK interfaces with this option here, and then you can specify for instance, the Intel MKL64 ILP interface, but standard you would use the LP, not ILP. So this is a common mistake that people try to link with ILP, but then every integer passed to BLAS or LAPACK is 64-bit. And this is how you enable or disable external dependencies to STRUMPACK, like butterfly pack, Scotch, Parmetes, CFP, combinatorial BLAS, Slate. So I have this TPL, which stands for third-party library, enable Scotch is on or off, for instance. This is how you install Metis, but you can also see that in the config script in the manual install folder. This is how you can install STRUMPACK using SPAC. You first have to clone the SPAC Git repository, and then run this setup script. You have to configure your compilers, and then you can simply type SPAC install STRUMPACK or a specific version, or enable or disable certain variants like Scotch or Parmetes and so on. And then you can build with GPU support. And then finally, you can load the package. And then this is how to enable or how to install STRUMPACK through PETSc. You can add the download STRUMPACK option. But since STRUMPACK needs ScalaPack, you will also have to tell PETSc where to find ScalaPack and Metis. And I already showed this briefly. This is how you can use STRUMPACK in your own project through CMake. So you have in your CMake lists.txt, you just add this line STRUMPACK, find package STRUMPACK, and then you in the target link libraries, you specify the target STRUMPACK : STRUMPACK. Then you just run CMake using this CMake lists file. If you don't want to use this CMake way to build your project, then I recommend you just go inside the STRUMPACK build folder and do a make, for instance, make examples verbose equals 1. So it prints out exactly what build and link options are used to build these STRUMPACK examples. And then you can use those in your own project. I think that's it for now. Maybe we can have a short break here. And in the meantime, we will monitor the Zoom chat to see if people have issues installing the software and getting ready for the hands-on.
So one thing I want to mention is we have for this breakout rooms set up. There are 3 rooms for each of us, and then there's one room for just for drop-in if you have want some other discussion. So basically, suppose for your you have any problem with the software, you want to have individual help, one-on-one help, you can ask one of us, when we are not speaking. We can go to that room, we can take a look to answer individual questions. Are there any questions? We have a few minutes before we start the next session.
So Sherry, where is the breakout room located? I don't see any icon on my screen. Someone has difficulty logging onto the machine.
Breakout room is on Zoom. So do you see that? On the Zoom, at the bottom, right next to reactions, there should be a breakout room, the squares.
No, I don't see it on my screen.
Oh, Peter, do you see that? Or
yes, and I can also assign people to breakout rooms. So if you let me know who.
Yeah, I'm not sure whether it's because your Zoom was the earlier version of Zoom.
I don't know. I say I'm not a co-host. I don't know why. But maybe.
Oh, so I saw another message. It said, do not see the breakout rooms. I opened the breakout rooms.
I mean, there's an option. Is there an option to make it available for everyone?
I'm not sure. I don't think so. I wonder, is that only the host?
I believe so, yes.
Maybe, okay. So I'm not sure whether, Nicholson, do you know? How do we open this for everyone?
I don't know what else to do. I see one thing here. Oh, that's not it. Yeah, from where I see it, it should be open to everyone. Yeah, but a lot of people are reporting that they don't see it. Does any attendee see the breakout rooms? You can send a message or unmute yourself and let us know.
I mean, there's two persons saying they don't see the 3 persons saying they don't have the they don't see the breakout option.
Yeah, I'm clicking this breakout room icon. I don't see how to change the setting.
Can you make me a co-host so I can try?
So let me see whether you can.
Yes.
Okay, now you are co-host. So when you are co-host, you can see breakout.
Yes,
room.
now I can say it. Yes.
Yeah, but how to set up? All right. So while Yang is figuring out the breakout room, I will.
I'll ask the support team as well.
Okay, thank you. So we'll start the next session. Where's the PowerPoint? All right. So let me make this full screen. Okay, so now we are spending maybe 30 minutes to talk about the a little bit deeper dive of the sparse Gaussian elimination algorithm. Okay, so we first review Gaussian elimination to solve the linear system. The first step in GE is you do the diagonal element is a pivot. You do the scaling of using this diagonal element to scale into the row, and then use this column and the row vector to do this update to the short complement, which is of size n-1. So it's vertical column vector, row vector divided by the scalar dot product become rank 1 matrix updated into the B matrix here. And now you see that if alpha is small, so this division after this division, this rank 1 matrix elements could be very big, which dominates the original element in B. So that's not good because the regular elements size could be wiped out because of the floating point subtraction here. That's why you want to avoid having a small pivot here. And that's where the numerical pivoting comes into the picture. So partial pivoting in the way is that you along the, instead of choosing this scalar to do the pivoting, you probably want to pick the biggest element along this column. That's why people doing the row swap, so that to avoid a small pivot. And then you repeat this on C. The result of this will be the LU factor. But of course, if there's a pivoting, then you have a permutation involved, which we'll show you later. After the lower upper triangular matrices, then you do a two triangular system solve. One is based on L, one is based on U. All right, so the main thing is to want to exploit a sparsity. And when we talk about sparsity, there are two different kinds. One is structural sparsity, which means in your matrix, you have a lot of hard zeros, which you don't want to deal with, so don't store them, don't do operation with them. And in this case, for many 3D discretized PDE problem, you actually could get the LU to be order of n square instead of n cubed if you treat it as a dense. But on top of this structural sparsity, you can also add a data sparsity. That's more, later people started to realize you can do this also. And this involves approximation. So that's the whole STRUMPACK. A lot of these compression algorithms are, on top of structural sparsity, you do the data sparsity. And then if depending on the situation, so depending on the applications, the matrices, very often you can knock down the complexity of LU from n squared to nearly order n with some polylog factor there, okay? And in SuperLU, we only do structural sparsity. In STRUMPACK, we have both the structural and the data sparsity. I see, Yang, you figured out the breakout room, is it?
Well, I think Austin said in the beginning of the meeting, you need, choose the option to allow everyone to be visible. But I guess that requires everyone to log out. Maybe you can just make everyone co-host.
Okay, I see.
No, so it should be when we are opening the breakout room, there was an option to select whether we want to allow people to join the rooms.
Oh, okay, I see.
So I just changed that. Yep.
Okay, I think people are seeing it now.
Yeah.
All right, yeah, so if you have need, feel free to ask any of us to go to the breakout room to help you with the code, etc. Okay, so let's continue. So I'll start with a very standard matrix from PDE discretization. A lot of us are familiar with this. So this is the Poisson equation in 2D. In the continuum form, it's written this partial differential equation, right? So you have xy corresponding to the space, and the right f is the right-hand side, then there's some boundary condition. And if you use a standard discrete 5-point stencil discretization, then you have this is your each point here, it's related to the 4 neighbors. You do this approximation. So each equation is something like this. And then putting all the equations together, you get a matrix A, which looks like this. So it's on the diagonal is 4 and 3 other diagonals, which is -4, okay? All right. So for this matrix, you actually can do, suppose we just use, this is the 5-point stencil, the lighter blue ones there, right? You can do Gaussian elimination in this order. And then you'll discover that all these in the middle used to be zeros, and now it becomes a non-zero. It's all filled except the upper few of them. And it becomes a fully banded matrix. And of course, it's still very regular. If you look at this, you can say, I can design a banded solver to do this, okay, to take all the fields here, and then it's a banded solver. So LAPACK has this banded solver to do that. And then you can do algorithm analysis. The filling in this case is actually order of n to the 3/2, and the flops will be order of n squared. So on the right here, I'm using, it's the same matrix, but I use a different ordering of the I use minimum degree ordering. And then you see the pattern will be different. So this light blue one is still my original non-zero, and the red ones are the filling. And now I see the filling is 207 versus 233 on the picture here, if you stay this order. And you can show that actually for 2D discretize the problem, actually for many planar graph from a finite difference application, the filling in 2D is order of n log n. It's much better than n to the 3/2, and the flops is also reduced. So it's a big benefit if you can shuffle your matrix order. And that leads to the big question is in sparse LU, you have this filling phenomenon. And no matter what you do, you start with, no matter what order you change. And very often you get this red dot field. So this red dot, for example, it's because of you have a original non-zero here, original non-zero here. When you do the dot product, they generate this non-zero. Originally it's a 0. So all these red dots, original position are 0, but it becomes non-zero. And another thing is these red dots, when the matrices gets bigger, they propagate. Yeah, so it's, this red dots could produce that one and will continue. So it's a chain effect. In fact, if you're trying to find all the red dots in graph term, it's in the non-symmetric case, you find the transitive closure of the original graph. Then you get all the red dots. All right, so let's see. Then we'll need to represent the sparse matrix. We don't want to store zeros. So what we do here, we use a compressed row storage. And this is my picture with I labeled only the non-zeros. So in this compressed column storage, you just store, one-dimensionally linearize the non-zeros. So you have first column one. So sorry, this is compressed row storage. So you go row-wise. First row 1A, second row 2B, C, and the third row, etc. So just having this one-dimensional value is certainly not enough. Then we need the metadata structure. That's what in sparse case, you always have a different metadata structure to interpret your numerical values. So in the compressed row storage, for each of these non-zeros, we have a column index in corresponding to the original matrix A in N. So for example, if you look at element E here, the column index is 2. It's in the second column. And so for each of these non-zero, you have a corresponding column index, and then you have a row pointer to point to the starting position of each row. And as you can imagine, because this is row-wise storage, so the algorithm, it's good for the algorithm which traverses the matrices in row, okay? And then if you look at this template book for linear systems, there are a lot of different storage representation. And now let's see, what do you do with the sparse case? In the sparse case, you can, at least from user input point of view, you can do the same thing. You have, let's say you have 3 matrices. Then you usually, for a lot of packages like PETSc, our direct solvers, Trilinos, we all support these kind of distributed compressed row storage. So you partition by block row, and each process has a part of the whole matrix. And within each process, you use a CSR format or CSC format. So that's from user point of view, it's relatively easy. And B usually is a dense matrix. So it's dense, could be column-wise standard dense format. But the bigger question is internally, which is not visible to the user. We actually have something more performance, high performance related storage, which is quite complex. But the good point is that you, from user point of view, you don't need to see them, even though it's output. All right, so let's see the small example of this. Will be in the SuperLU disk, the Fortran example, you can see a 5 by 5 matrix. So I divided into P0 and the P1. And so A is distributed on 2 processes. So from P1, process 1 point of view, the number of non-zero local is 7. I have 7 non-zeros. And M local is the local, how many rows of the equations I have is 3. In this case, and the first row I start from 2. So in SuperLU, it's a C language. So everything, the indexing is 0 based. So the first row is globally it's 0, 1, 2, 3, 4. Okay, so that's why on process 1, the first row is 2, and the values will be just compressed row representation. Okay, let's move to the solver phase. And as I mentioned, this filling that makes the whole solver landscape very complicated compared to dense LU. And usually we need some pre-processing steps before we actually get to the numerical factorization. So the first pre-processing step is reorder equations to minimize fill and maybe to maximize parallelism. And I showed in your earlier cartoon that with this 5-point Poisson equation, if you do natural ordering, you will get a lot more fill compared to if you do minimum degree or massive dissection ordering. So that's a big deal. And ordering is, this part is purely a graph algorithm, and to find the optimal is not a polynomial time you can find, so it's NP complete. So every algorithm we use are heuristics based. And another pre-processing is to, once you fix the order, you predict the filling positions in the LU factors. And this is often called a symbolic factorization. And it's pretty fast because it's kind of a mimic a GE, but then you work with just the graph, and also you can use some technique to shrink the graph like a supernode, which we'll see soon. And then you got a very sparser graph, like say a smaller graph compared to the original matrix. So it's usually pretty fast, but it's harder, all these things, they are very hard to parallelize on the GPU. And then another pre-processing step is you need the data structure, good metadata structure for L and U, and different packages they use internally, they use a different data structure. After all this is set up, finally you do the numerical factorization, and then the triangular solve. This is numerical phase. So in the parentheses, I put it in the roughly time. This is purely just the estimate. It can vary a lot depending on matrices. But I would say for the most cases, the numerical factorization is very heavy load. And that's why people spend all the paper, most of the papers are about how to speed up this process for strong scaling for GPU. Okay, so I'll mention quickly about this numerical pivoting, why it's become a sticky point for sparse LU. So the goal of pivoting is to control element growth in the LU for stability. And as I showed in the first slide, when you do the division by the diagonal element, this alpha, if alpha is tiny, then you get huge blow up of the element. That destroys your stability of the algorithm. So that's pivoting is important. And then I will show you the partial pivoting, how it works, what's the impact for the sparsity. So let's say, suppose at this stage of elimination, I have only 2 rows, 2 non-zero rows, and then my current pivot is S. And let's say this element is small. So the biggest element along this column is B. So I want to, for partial pivoting, you would want to swap these two rows. You want to use B to be your pivot. But then you can see the difference in terms of sparsity. So if you use S, this row as pivot, then you do the outer product of this row versus this column, then the impact on this row will be you generate two non-zeros here, right? It's because of these two guys. On the other hand, if you use B, this row as pivot, then the impact on this row will be you will generate three non-zeros. So depending on at each stage, each step of elimination, depending on which pivot you choose, your sparsity pattern will change dynamically. And that's very unpleasant for sparse case. So that's why, partial pivoting, it's difficult to do for distributed memory. And we did this in sequential and shared memory called partial pivoting, which are very good, numerically. But for distributed memory, what we do, we actually use a graph algorithm to do static pivoting. We use a matrix A based on matrix A instead of based on the dynamic LU. We use matrix A to find the maximum element to pre-permute maximum element along the diagonal. And while doing the LU, we don't change that row permutation. Row order is fixed. So numerical pivoting was done before numerical factorization. And it's a we call this a static. And as you can see, it's not dynamically adjusting based on these SB elements. So potentially you could have a less stable algorithm. All right. Another thing is about ordering to reduce field. So this picture is a classical textbook example. Is suppose you are presented with this matrix, a 5x5 matrix, and you just do Gaussian elimination in this order. After the first step, you will get everywhere else will become fully populated. So that's just the nature of the algorithm. So you become, no matter how large your matrix, how small the matrix in the end, after first step, you become fully dense. So that's not good. And then on the other hand, if you are clever, you use a two permutation. This two permutation is the same permutation symmetrically. So you symmetrically permute these, change the rows, basically reverse the rows and reverse the columns. Then it becomes this order. And then when you do elimination in this order, every zeros is preserved. So you don't generate any field at all. So it's order n, no matter how large the matrix is. So that's the important thing of the ordering. And then there are two kinds of ordering algorithm. One is the greedy algorithm. It's called a minimum degree. And it's very easy to describe from the picture here. Suppose right now you have a picture of the matrix at this stage, and then the graph you look at the graph connectivity of this vertex 1 is connected to the IJKL. For others, it's symmetric, okay. And then from the matrix point of view, when you eliminate this 1, because of this dot product, outer product of this column vector, row vector, everything else becomes fully dense after first step of elimination. And from graph point of view is after you eliminate vertex 1, the neighbor vertices become a clique in computer science term. It's fully connected. Okay, so that's essentially the elimination game of Gaussian of minimum degree ordering is you start with your graph, and then you first step, you pick a vertex with the smallest degree to do the elimination so that your clique generated is the smallest at that stage. And then you forget about that vertex, update your graph. And then you start for the smaller graph, you pick up the vertex with the smallest degree again, and then generate another clique updating the graph. So that's the process. And of course, the implementation, there are a lot of details. So for example, how do you, when you have multiple vertices with the same degree, how do you do tie breaking? And then how do you implement this efficiently instead of like doing each one step, as Gaussian elimination? So there's something called quotient graph, and also you can speed up with approximate degree. A lot of techniques there. Then another idea is to do the top level, not the greedy algorithm, but with top level, we want to do optimal. So this is the idea of nested dissection. And again, I'm using this model problem for discretization from PDE, for example, my first picture is if you look at the geometry, your 5-point stencil looks like this for 2D Poisson equation. So what you do is you try to find some set of vertices, do we call this a separator, to partition into two parts. And then after this partition into separate into two parts, then your Gaussian elimination for that part has nothing to do with Gaussian elimination on this part. And that's the idea, is try to localize your field from top-down approach. So the ordering, this is the partitioning part, so you can keep recursively doing the partition. For this part, doing the separator here. For that part, doing the separator here. And then with this partition, you can order the matrix following this partition. So the top level partition, I will put that in the end. And then the second level partition, I put that here. So the 10 partition is here. And this 20 representative, I put it here. And then continuously, you can do this recursively. So then you can see that from the matrix term, if you look at my elimination of this, the 10 part, this block, when you do elimination, it won't touch anything corresponding to this 0 block. It will generate some filling for this separator corresponding to this separator part. So you do localize the non-zero part, the non-zero propagation is essentially following this separator tree. So the non-zero will go up to the parent ancestors, but they won't go to the sideway to affect the siblings or the other branches of the tree. And with this separator tree, it's actually very powerful. So that's not only reduce the field, and also it helps you to do parallelism. So you can naturally have also different processes assigned to different branches of the tree. And the nested dissection I talked about was based on the regular mesh, but you can do this for any general graph. So for example, here, the picture is any general graph. The main thing is to find the separator. And after the separator, for each of these different parts, you find another separator. So you reorder the matrix in here. So the big research area is how to find the separator. You want the separator to be as small as possible, so that if separator is small, then AP blocks are big. So your 0 blocks are maximized. So that's the main goal of this optimization. So there are a lot of papers on that. And then you can see the nested dissection ordering. This is basically the picture of original matrix A in banded form. And then if you use the nested dissection ordering, the original matrix A, the original matrix A looks like this. And the filling is restricted within the separator part. So these are the red are the fillings. All right, so I'm going to skip this, how do you do ordering for LU with the non-symmetric patterns, especially if you do partial pivoting. So there are some techniques for that. You can probably read yourself. And now it leads to the question with all this pre-processing I mentioned. So in the end, actually, you don't solve AX equals to B. You solve this transformed linear system usually. So in this transformed linear system, you first probably do some equilibration, diagonal scaling to make improve the condition number. And then you do the row permutation. In SuperLU, we use the row permutation for numerical pivoting. In STRUMPACK, it's using the column pivoting, column permutation for, so it's this PR is on the left, right here for numerical pivoting, but it's the same idea. And then after that, after pivoting order is fixed, you run the sparsity reducing ordering, symmetric ordering. this needs to be symmetric so that you don't destroy your good diagonal, the big diagonal you have discovered earlier. And then your right-hand side needs to do this transformation. And then first you solve the y, and then you transform this y into, after these two transform into x. So it's a lot of steps there, okay? And all these options, they can be, user can choose. So whether you want equilibration or not, row permutation, we can do the, MC64 or parallel, the heavyweight perfect matching, which is a parallel algorithm. And then if you have a clever idea of what's the row permutation should look like, you can input this vector. This is just a vector of from 1 to n. Similarly, for column permutation, we have a lot of options. For large matrices, the default one is the metis is good. But if you don't want to use the metis, you don't want to install metis, you can use all the other options. And then I will talk briefly, I think I'm running out of time at this stage, about the different types of algorithms. So you have probably heard about supernodal algorithm and the multifrontal algorithm. Also on the vertical axis here, we have different matrix properties. All these different properties actually could dictate how complex, how your metadata, internal meta-LU data structure needs to be designed. So it's a very complicated issue. So for the matrix property, you can have a symmetric or positive definite. For and then if you go down to even more general, you can have a symmetric pattern and non-symmetric value. And the most general is non-symmetric. Everything is non-symmetric, both pattern and value. So there are different codes to do this. And the big thing is that depending on whether you want to respect the non-symmetric pattern, then your underneath the graph is actually has to be DAG or tree-based. So these are the different codes. So for example, for mumps, people are familiar with, they stay with symmetric patterns, so it's tree-based. But for UMFPAC, which is from Tim Davis, it's a multifront code, but they stay with the non-symmetric pattern, so it's a DAG-based. So it's a, it's orthogonal issue, these two axes, whether it's a supernodal, multifrontal, whether it's DAG or tree-based, it's really depending on whether you want to respect a symmetric pattern, non-symmetric pattern. All right, so that's the picture, basically explaining what I said in the previous slide. If you want to respect a non-symmetric pattern, it's going to be DAG-based, no matter whether it's supernodal or multifrontal code. But on the other hand, if you want to symmetrize the pattern, then you could have a simpler structure, which is tree-based. And the fundamental mathematics is this filling propagation. So if you symmetrize, you potentially could allow more zeros. Potentially, you can get more filling to deal with. All right, and then we'll just talk about the supernode. The supernode is, this was started in the early days when the machine, at that time there was no GPU, but it's really deep memory hierarchy. So you want to increase the arithmetic intensity. So what we do there is for the LU matrix, you try to find the consecutive columns, for example, in this case for L. They have the same row structure, then you can group them together as a super vertex. And in the matrix form is the dense subblock of the matrix. And you can imagine that these dense subblock, you can squash them, store in memory in the contiguous value. And also you only need to store the index, the leading column of the supernode. And it also helps a lot in the graph algorithm for the symbolic factorization, because these 4 vertices, when they become a supernode, they are fully connected. So in the graph algorithm, symbolic factorization, etc., you can speed up, you work on the much coarser graph of a smaller size. And then I can talk about this distribution. This is internal, based on the supernode partition internally. the LU data structure looks like this for the SuperLU. And then for process grid, we use a 2D block cyclic layout. So for example, for 6 processes, you arrange this as a 0, 1, 2, 3, 4, 5, and then you just give 0, 1, 2, 3, 4, 5, replicate this template across the global matrix so that you can imagine with this distribution, you have a good load balance and your communication is restricted along the process row or along the process column. And this data structure, it's outputted, but usually users do not need to worry about this. It's a lot more complex than compressed, distributed compressed row for a matrix that you need to deal with. And similarly for this tree-based, multi-frontal code, the tree-based code, you can do similar kind of 2D block cyclic layout. In this case, every separator is a dense submatrix, and then you can divide your whole processes, along, say, half of them to here and some part of them to the other side, depending on your weight. You can do proportional mapping of the processes. And sometimes if you have 7 processes somewhere, it's not very good to do 1/7 grid, right? You can say, I leave out one matrix. For this part, I only use 6 processes to make this 2/3 grid. So this is the flexibility that STRUMPACK provides. And I just want to mention that, we're talking about supernode frontal matrix. Essentially, all these concepts are approximately the same thing. Supernode is essentially a separator, and the separator is essentially corresponding to the frontal matrix in the multi-frontal term. All right, so I'll summarize the algorithm complexity. So we still look at, it's difficult for sparse matrix to analyze any, say, social network graph. It's just impossible to do closed form analysis. But our analysis, we can use the PDE with regular mesh. It can be 2D or 3D. So in the dense case, we all know that the operation is n cube. And in the sparse case, it depends on how how do you organize things, what's ordering you are using. So in the 2D, for this regular mesh, actually nested dissection ordering, you can prove you can achieve optimality. But even for optimal ordering nested dissection, if you do exact LU in the 3D problem, you will get an n² operation, and the solve flops is better, but the memory is n to the 4/3. And with the STRUMPACK, with low rank compression, you could knock down this flops essentially to n to the alpha. Alpha is smaller than 2, and then with some polylog n log factor. So sometimes alpha could be 1, so it's essentially a linear time algorithm. It's not always, but usually it's faster than this. And similarly for the memory and the solve, it's essentially linear. So that's the benefit, the power of using this hierarchical low rank representation. And the last thing, I think it's almost the last thing for this part, is I maintain a survey of sparse direct solver codes. And it's useful because as you can see that to write a good direct solver, it's very labor intensive. So over the years, people have developed various code. And then in this survey, in the paper, I divided into 3 chunks, so the serial, parallel, shared memory, and distributed memory. And the serial code, for example, this from Harvard Library, it's started developing many years ago, but it's actually still very heavily used by some community. For example, MA57, this is symmetric indefinite 2x2 pivoting code. It's very useful for the optimization, the grid optimization community, KKT type of system. We don't see any good, from algorithm point of view, we don't see any good alternative to this kind of algorithm. But of course, it's difficult to parallelize. So that's the, it's still remain pretty open question. And then as you go down to more distributed memory, there are fewer code. And in this table, I also labeled which code has a GPU capability. And I would say there are not so many code currently with a GPU capability. So this is some reference. I think that's for this section. So I, almost 10 years ago, I gave a 10-hour lecture at the Jingalop Summer School. And then I wrote an extended summary about all this landscape. So in that lecture, I actually went into very detailed about how to do vectorization, how to, various parallel aspects. You can take a look. Are there any questions so far? Then I have maybe, I think I have maybe 10, 15. Peter, do I have like 15 minutes to do some?
Yes, go ahead.
Okay. Are there any questions so far? All right. So what I will do is to talk about the recent SuperLU disk development in two aspects. One is GPU, one is the communication avoiding. So this is specific to SuperLU disk. So in SuperLU disk, each step of elimination, this is your picture of the LU matrix globally after you factored it. It looks like this, sparse. So within each step of elimination, by the way, so this structure you have to identify using at the symbolic stage to set up the data structure, but numerical values are populated step by step. So within each step, we need to gather this the skyline storage of U into a dense matrix. And the L matrix, here I say gather, but in fact in storage, they are already stored like this. So there's nothing needs to be done, but gather is really for this. After you get these two dense submatrices, and then you do the gem operation to get this V matrix. So this V matrix looks like a dense, but the indices, they are actually sparse. So you have a different row indices. So what you have to do after this gem is to scatter into the destination to prepare for the next step of elimination. So that's what's happening at each step. So essentially each step you have a gather phase, and then gem phase, and then scatter phase. All right. So as you can imagine, gem is good for GPU for any parallel machine, but the scatter is problematic. All right. So our first attempt was actually for GPU was a long time ago. It's in this Europart 2014 paper. So what we do is we slice this, we only offload the gem onto GPU because scatter is a bit more complicated. So you have a CUDA side, you have a CPU side, and on both sides, the CPU side will do the scatter operation, and GPU side will do the gem operation. But you have to slice this gem into multiple streams. Otherwise, it's going to be the communication between CPU and GPU will become dominant. So using this slicing, you can overlap the communication phase with the gem operation on the GPU. So that's essentially what's happening. It's you have to use multiple streams to get these to work efficiently. And in the code, there's a parameter called the number of CUDA streams that you can change to essentially change this number of slices you are doing. And that's relatively, at least from algorithm point of view, relatively, it's pretty easy to conceptually, it's easy to think about. And now if you look at the performance of this 2D algorithm plus GPU, this was done earlier on the Oak Ridge Titan machine with 1,000 cores with 64 GPU. So what's the picture here showing is the red, each bar has a red part, which is the panel factorization. And the blue one is the short complement update. So the gem is in short complement update, which is accelerated by GPU. and lower number is better. So you can see that this is with a different OpenMP, MPI, and the mixture of different optimization, I think. And then you can see that with when we have more and more optimization techniques, you can get a better and better speed up. But in the end, this panel factorization becomes a bottleneck. In fact, it's most of the time it's doing the MPI communication, and you sped up a lot of a gem, but the rest is becoming dominant. So that's why it motivated us to look at the communication avoiding. And communication avoiding, you probably have read a lot of papers from a dense matrix calculation, like dense QR, dense LU, etc. And dense gem, of course, people have worked a lot on dense gem. And one of the techniques is very promising, is to organize the processes in 3D. And then so instead of 2D process, we have P, X, Y, then we have added the third dimension of PZ dimension. And this PZ dimension, in dense case, you replicate some of the dense matrices along that dimension. Using more memory, then you communicate less. That's essentially the trade-off between communication or local memory storage. So that's for dense matrix multiplication. And we borrowed that idea for sparse LU, and it's similar, the process is organized into this fashion. And then you can see, so in sparse LU, we did something along the Z dimension. It's really just to replicate the short complement update, to split the short complement update along the Z dimension, the multiple layers of processes. And in fact, we can prove that the asymptotically, the communication volume is reduced by this square root of log n. And also asymptotically, the latency is reduced by log n. So that's why this is a asymptotically better algorithm. It's not just a constant factor. And then we have a pretty good result. So for example, for the planar graph, we can get a 27x speed up on 24,000 cores, which is very good. And non-planar graph, usually is 3D graph, you get a slightly smaller speed up. The main reason is because the separator in the 3D case, it's very big. So in our case, for each separator, currently we are not doing the 3D algorithm. Our 3D algorithm is only along the separator tree. So our next step is for each separator, we have to do 3D algorithm. So that's the future work. But still, if you look at this picture, it shows the teraflop rate. And this picture is change the organization of the 2D process grid and the third dimension. So along the diagonal here, where I'm using the same number of processes, but I'm just trading off for PZ with the PXY. So if PZ is 1, only 2-dimensional case, you only get 2x speed up, even though you throw in 32x processes. On the other hand, if you go up to the process PZ, even with the same process number of processes, you can see by this point, you get a lot better speed up. So that's the idea of 3D. And then for this 3D, we also added the GPU. Here we are doing more GPU offload instead of just gem. So basically this side is GPU accelerator, this side is CPU. So for each short complement, you divide into 2 parts. One part is on CPU, one part is on GPU. And how much do you want to put on GPU? There's a parameter which I will show you the influence of that parameter. You could get you can set the maximum buffer size, that parameter. It depends on your GPU memory. Suppose your GPU, in the early days, GPU memory is very small. So your maximum buffer size is very small. You can only offload a small chunk. But nowadays, the buffer size, you can set to very big, like even 2 gigabytes, several big gigabytes, then you can offload more to here. And this picture just shows we were trying to overlap on the CPU side, the accelerator side, communication between them. This timeline, we're trying to overlap the operation. And then with this 3D algorithm plus GPU, we see something like 3x speed up. This is the parallel when 2-dimensional process is set to 8, and then PZ dimension set to 32. So total process is 32 by 8. That's 256. Okay, get a very good speed up. Now, one thing I want to point out is when you get increasing the number of processes, GPU effect is much smaller. This is because you become communication dominant. Your local part, no matter how much you accelerate, it doesn't matter anymore. So that's the thing is with the GPU, it's accelerate your local part, but it doesn't help you in terms of communication. It's still a lot of work needs to be done to reduce communication for large scale. And I will, how much time do I have, Peter?
Well, I think we can be flexible.
No, we want to stay on the schedule. Like
well,
10 minutes?
Then, yeah, we have a 10-minute break planned right now.
Oh, right now already starting?
Yes.
Oh, okay. So I can let you read these slides about the tip for debugging performance. So the code, we have a default, all the parameter, we have a default setting, which is reasonably good, but certainly not optimal. And then you read our algorithm, you have some intuition, then you can tune some parameters. But that gives you maybe 10, 20% better. But what I'm going to show you here is if you use auto tuner, you can actually get a lot more benefit. So this auto tuner, we have a tutorial this afternoon about this GP tune. It's also 3 hours tutorial with the hands-on. So your matrix, what I'm showing you here is two objective optimization. I want to minimize time, minimize the memory. And then in this case, I have several parameters, column permutation, maximum supernode size, the relaxed supernode, and the process row size. The column size will be, the process column configuration will be derived from the row if you fix the number of processes here. So this auto tuner is using Gaussian process to build the surrogate model, and then it's iteratively sampling your configuration, parameter configuration space, and iteratively improve this surrogate model. So in this, suppose in this case, I have 5 parameters. Imagine that if you do exhaustive search, it's going to be, 5 to the 6 to the 5 number of configurations. But we only need to use 100 samples by using this Bayesian optimization clever technique. Then you can discover the best configuration. This is a Pareto front of the 2 objective functions, so which means it represents the trade-off between time and memory. If you want a smaller memory, then you have to increase time. If you want to, that's the situation. And in this case, so all these dots, they are all the 100 samples. The default is actually on the Pareto front, so it's good. But if you want a better time, then you have to, better time here, you have to use more memory. So that's the tuned result compared to the default. You do get better. But then thing is, you realize that suppose you want the best time, your tuned maximum supernodes NREL is actually some number which is non-intuitive, but it's dependent on your architecture, of course. And so this is 3D code with CPU plus GPU. And here, as I mentioned, we have this maximum buffer size. It actually, when you tune this parameter, so here we have 1, 2, 3, 4, 5, again, 5 parameters. When you tune this parameter, you do get a different time and memory requirement. So it seems like with a smaller this maximum buffer size, which means you give a little more work to CPU, less work to GPU, so that they balance the better. So then you get a better runtime here. And as you can see, with this auto tuner, you can get the speed up could be like 4 times difference between the default. So this tuned one is 4 times better than the default one. All right. So I don't have time to do the hands-on on the computer, but I will show you on this Frank system the result. And let's see, let's maybe look at this AMD, because people are getting, everybody knows the CUDA, NVIDIA, so AMD is still relatively new. So I have 3 matrices here, and this is the, how do you run this code? The 2D code, the PD drive, 3D code is 3D. And then by default, we have this environment variable is set to 1, so use the GPU, but you can set this to 0 to turn off GPU. So let's take a look at one example here, torso 3 here. For the 2D, for 3D, using GPU, there's no benefit. For 2D, using GPU is worse, okay? But then if you look at another matrix here, for 2D, using GPU is slightly better. But for the 3D code, using GPU is a lot better, because this one, we're actually offloading a lot more stuff to GPU, and this 2D code only offload the gem. So it's on this machine, on the AMD, only offload the gem. It's not so great. It's not very beneficial. Let me see, what do you have? Yeah. So this is the last slide. In fact, I will just, you can read the slide. I can actually just show you the code to point you to what to read in the code. So you go to the SuperLU dist directory, and then you go to example. There is a README. So every directory, we should have a README, so you know what to work. So the README here, there's the first bullet here is about 2D algorithm, 3D algorithm. But what we need, I want to demonstrate, but I don't have time, is really you can have, depending on your usage situation, you can reuse a lot of the pre-processing step. So for example, if you solve the same linear system with different right-hand side, then you don't need to do the reordering, you don't need to do the symbolic factorization every time. So your factor LU could be reused. And for the next case, this example is you solve the system with the same sparsity pattern. Here, I'm reusing the sparsity reordering. So your minimum degree meters could be run only once. And then you can reuse also the, for this case, you reuse the numerical value. The numerical value is similar. You can reuse the numerical pivoting. And the last example 4 here is to show you that in your big application, you can divide the processes into multiple groups. So you can run the multiple parallel SuperLU dist different instances parallel simultaneously. So that's how you do the MPI subgroup business. And the exam, maybe I'll just show you one example here. So the call is, so a lot of setup here. The driver routine is this PDGS SVX, okay? So here, I'm sorry, this is the second call. So the first call is, I set a number of right-hand side to be 1. This is the first call. It will solve the linear system with all the default options. And then here, I'm changed the factor, this option. I say it's already factored. So I tell the same driver. I call the same driver the second time, but this option said that it's already factored. So inside this driver, I will just do a triangular solve. So essentially the most powerful part is this options. You call the same driver, but then you're depending on your different option setting, then your internally driver will do different thing, will reuse a lot of your work that was done previously. So that's how most of the this reuse is set up in this way. So I think you will need to read the these examples, and then the user guide. We have details about this. So I don't have time to do the demonstration now. All right, so I'll stop here. Sorry, it's long. Any quick questions? Okay, so are we?
Actually, I have a question. Sorry, I tried to raise my hand, but
yeah,
you had a few graphs about performance. You went very quickly over. What does it mean in practice? It means for certain matrices, there's no benefit from running on GPU.
Yeah, well, so
can you
so
say
for
more
example,
about when it's beneficial and when it's not? What should we look for?
It's hard to say. So it's very complicated. Where there's no, we have a theoretical formula for the communication count but for GPU we don't have any theoretical formula even to guide the people. So that's why we're talking about all these auto tuning business. And as you can see that in this table, especially for 2D algorithm for GPU, it's probably you don't get much benefit. But for 3D algorithm in the future, we offload a lot more stuff, you get more benefit. So it's a trial and error for performance.
Okay, thank you.
All right, so let me stop. I think I'll stop share. Let's see, what do we have? Peter, are we still in the break or?
Yeah, according to our plan, the break was from 9 to 9:10.
Oh, okay, so it's almost there. Do people have any general issues with the software, the hands-on part that may be interesting to share with the other people? For example, if you have something you couldn't get it to work.
I had a question. My name is Nari. I'm from Altair. I joined this chat in the middle. I'm sorry. Did you share some source code here with all the people? Some sort of a directory structure? Because it looks like you were showing us the code in the last couple of slides. And
yeah, so do you want to get on the machine?
I was just curious what that was all about. I'm sorry I joined it late. So
that's okay. Yeah, so of course you can download the source code from the GitHub, but this the code I'm showing here is on the on this Frank system. This one machine is authors, the server, and they do have two types of GPU. We're doing the hands-on on this machine.
I see.
If you want, we can assign you to one of the student account. You can get on the. We have so let me just show very quickly.
Actually, that's okay. I'm just.
So right now, I see we have these people assigned to the student account.
That's nice.
We still have if people still want to get on, we can assign. And the instruction is in this document, which in the Google folder. in the beginning how to log on all these machines with.
I see.
Yeah.
Okay.
I can send you the. I'll put the link of this folder again. If you want to just put in the chat, I can assign you to one of those accounts.
Okay. Thank you. I appreciate that. Yeah. Thank you.
Peter, if you are ready, I guess you can start. Or
okay. So now I'll talk more in detail about STRUMPACK and the algorithms used in STRUMPACK and the interface, how to use it, and do some hands-on. So STRUMPACK is a multi-frontal sparse LU solver. I'll go over this very briefly because Sherry explained most of this already. So I can explain this idea easiest using nested dissection ordering, but we can also use other orderings. But the nested dissection idea clearly illustrates this separator tree. So in nested dissection, you first find a node separator for the graph corresponding to the adjacency structure of the sparse matrix. So the separator, for instance, these red points that's the root separator. If you remove those nodes from the graph, then the graph splits into two unconnected components. So we get a binary tree where each sub component corresponds to a subtree, and we recursively find separators in there. And typically, because we keep dividing the mesh into smaller subgraphs, the separators become smaller and smaller as you go down the tree. And for each of these separators, we have a dense matrix in the node of the tree. And this dense matrix this is called a front. And this front is partitioned into a 2x2 matrix, where the top left block corresponds to the actual separator. And the 2-2 block, for instance, this block here is the Schur complement update, and this is temporary storage. This is only kept in memory to compute this Schur complement, and then this is passed along the tree to the parent. So this block is then scattered into the parent node. And so to do the sparse LU factorization, we have to traverse this tree, the supernodal or the separator tree, from the leaves to the root. And in each node, we have to compute an LU factorization of the top left block, then do some dense triangular solves with these lower left and upper right blocks, and then we can compute this Schur complement update and pass this to the parent. And after this is done for all of these nodes in the tree, we have these sparse LU factors, and we can use that to solve a linear system using forward and backward substitution by again traversing this tree first from the bottom to the top, and then from the top to the bottom again for the backward solve. So it's important to realize later on for tuning the algorithms that typically these matrices get smaller as you go down the tree because the separators get smaller. So very briefly here, the algorithm, we do some pre-processing, we compute this ordering. This P matrix is the ordering defined by the nested dissection algorithm. And then we loop over each node in the separator tree from the bottom to the top. First, we construct this dense matrix in the node of the tree, which has contributions from the original sparse matrix, and then this operation denotes a scatter operation. So we add this Schur complement from the lower levels in the tree into this front. And then we compute a dense LU, do this dense triangular solve with L and with U, and then finally compute this Schur complement update, which you then pass to the parent node. And in STRUMPACK, we will approximate this F matrix in the different nodes of the tree using a rank structured matrix. So that will be used to reduce the complexity of these operations here in red. These are dense linear algebra operations, which scale as n cubed with the size of f, and f can get quite big. If you have, for instance, a large mesh, then the size of f here is the size of the separator. So Sherry also already showed this slide. So this is how we do the parallelism in STRUMPACK. So we have this binary separator tree. At the root front is divided over the entire communicator using the 2D block cyclic layout used in ScalaPack. But we can leave some processes idle to have a better distribution, a better load balanced system. And then we split the communicator proportionally based on the sizes of the subtrees. And finally, until we reach a single processor, then we can use OpenMP task parallelism to traverse the rest of the local subtrees. So briefly about the GPU implementation in STRUMPACK. For the GPU implementation, we will traverse the levels in the supernodal or the separator tree. We will traverse this tree level by level instead of recursively traversing it. And then we can use so-called batched dense linear algebra operations to handle every node on the level with a single batched call. For instance, here we can do the dense LU factorization for each of these green matrices with a single call, a batched LU. The problem is that there are no variable-sized batched LU algorithms available yet. We're working with the Magma team to add such a routine. So since that's not available yet, what we do right now is we have our manual batched implementation for very small matrices up to 32 by 32, and anything larger than that we handle directly with QBLAS or QSolver in a loop with multiple streams. But this can still generate quite some overhead because this binary tree can get very wide at the base. In the SQL DPC++ code, MKL1 API does have this variable-sized batched routines. For instance, the GETRF batch is a routine which takes in an array of pointers to matrices stored on the device, and they can be of different sizes. So we also pass an array of sizes, and this does the LU for all of these matrices with a single call. But these are not optimized yet, so performance isn't super yet. I already also showed this GPU result on a single GPU for a 3D mesh. So we get quite good performance for larger problems, up to here 7 teraflop. But also you can see the performance drops off for smaller problems. So there is some overhead of offloading work to the GPU. For the very smallest problems, just staying on the CPU might actually be faster. But we've worked very hard to optimize also the case for the small problems here by doing as few memory allocations on the device as possible, and reducing as much the synchronization overheads and using these batched calls and so on. Here is performance results for the multi-GPU performance. So for multi-GPU, remember that in the distributed memory setting, we use ScalaPack for the distributed fronts. And then for the GPU code, we replace ScalaPack with Slate, developed at Tennessee. Slate has the similar functionality to ScalaPack, but can offload these blocks to the GPU. So here we take a 3D problem of size 100 cube up to 250 cube. And we run this on 1, 2, 4, or 8 summit nodes. And for instance, for the 200 cube problem, when running on 4 summit nodes, we use all 168 cores of the power 9, or we use all 24 V100 GPUs. And using the GPUs compared to only using the power 9 cores, we get a 10x speed up here. So that's from using Slate on the distributed fronts compared to ScalePack, and then traversing the local subtrees using CUDA compared to handling everything on CPU. So now I will describe the STRUMPACK Sparse Solver interface. So there are actually two main solver classes in STRUMPACK. One is this STRUMPACK Sparse Solver, which is sequential or multi-threaded using OpenMP. And then there's STRUMPACK Sparse Solver MPI dist, which, as the name suggests, is distributed using MPI. And these are templated on the precision, which can be float double, complex float, complex double. And then the integer type used for the sparse matrix. So this can be 32-bit signed integer or 64-bit signed integer. Actually, this class is now called just Sparse Solver and no longer STRUMPACK Sparse Solver because it's already in a namespace STRUMPACK. I thought it would be better to remove this, but there's still an alias called STRUMPACK Sparse Solver. So I'm sorry for the confusion, but so you can still use STRUMPACK Sparse Solver, which is also what it's called in the examples. And then we also have a mixed precision solver called STRUMPACK Sparse Solver Mixed Precision or Mixed Precision MPI dist. And this takes two precisions, for instance, float, which is used to do the sparse LU factorization, and a double, which is used to recover the solution in higher precision than the factorization precision. So this is the refinement precision. So we can then run the iterative refinement or preconditioned GMLS or BCG step with the single precision factorization as a preconditioner. So your input output can be in double, but internally it will compute the preconditioner in single precision. So here is how you would construct the sparse solver objects, STRUMPACK Sparse Solver for double precision. And this is how you can set options to the solver. So this SPSS is an object of the sparse solver class, and you can get the options object from that. So this will return a reference to an options object, and then you can set the matching. So the matching is the column permutation used for static pivoting for numerical accuracy. So this is calling the MC64 algorithm underneath, or combinatorial BLAS. I will go over these different options later. But for many problems, which are, for instance, diagonally dominant, you can disable this. So this matching will try to permute the matrix to put the largest elements on the diagonal. If your problem is, for instance, a simple stencil, your diagonal might already be non-zero and the problem might be diagonally dominant. So you can set this to none. You can set the reordering method for, this is the reordering for fill reducing. So we can set this, for instance, to metis, which is also the default. And then you can also set these command line options, so you can change some options from the command line. And then you can set the CSR matrix. So this is the standard row pointer, column, index, and value format of CSR matrix. In STRUMPACK, we also have a CSR matrix class, so you can also call set matrix and then pass an object to of the CSR matrix class, but then you would have to use STRUMPACK's classes. So this is more general interface, I would say. And then you can call this reordering phase, which will actually execute metis reordering, but this is optional. If you don't call reorder, then that will be called internally by the factor routine. But that's also optional. You can also just call solve, and solve will call factor if the matrix was not already factored. But you have to set the matrix first. So solve will solve a linear system AX equals B with the solution put into E. And then this is the Sparse solver MPI dist interface. So you have to include the Sparse solver MPI dist header, but the interface is similar, but now you use set distributed CSR, and you specify the distributed CSR format, which consists of a local CSR matrix on every processor, plus an additional vector dist, which describes the distribution. So each process P only owns the rows from dist up to, but not including dist P plus 1. And then row pointer column index and values are the local CSR representation. And this is the same. So you can look at some of these examples. For instance, in the singularity image. So remember, I had copied from Sparse STRUMPACK examples into this ECP tutorial folder, Saturn, if you're using NVIDIA. So now these examples are here. Oh, sorry. So here are the examples. You can have a look at these. Follow this along. So as I said, there's a CSR matrix class, which is then used to set the matrix. But you can also directly pass the column pointer row initials and the values to set CSR matrix. And then what I showed for the solve is you just pass a pointer to the right hand side and the solution. Sorry, the solution will be in X. But you can also solve linear systems with multiple right hand sides by defining this dense matrix, which is a STRUMPACK class, a simple wrapper around the column major stored dense matrix. Or you can simply specify the number of right hand sides, the pointer to the right hand side, the leading dimension of this right hand side matrix, a pointer to the solution, and the leading dimension of the solution, and whether or not you want to use the value stored in X as an initial guess. So this only matters if you are using an iterative solver. And then you can do multiple solves consecutively if you don't have all the right hand sides available at once. But for instance, you're doing some time integration or something like that, you can call this solve routine repeatedly, and this will then reuse the factorization. It will not redo the factorization if you don't set a new matrix, and the matrix is already factored, then solve will just reuse this factorization. You can also update the matrix values without updating the sparsity pattern. So in that case, when you update the values, but not the pattern, the factorization will be redone, but the reordering will not be redone. So ideally, this interface would only take a list of updated values, because these row pointer and column indices vectors, they need to be the same as the matrix which was previously defined, previously passed to the solver. But we ask that you pass these again. That's an implementation issue. But so these row pointer and column indices have to be the same as the matrix from before. So then if you call this with new values and then call solve again, the column permutation, so the MC64 matching and the METIS fill reducing ordering are not redone, but it will redo the factorization. So then for the GPU acceleration, you can enable this using the options structure, enable GPU or disable GPU. Or when you set the command line options, you can, when you run an example and you pass these options, you can just specify --sp enable GPU or disable GPU. And for now, in STRUMPACK, every MPI process can only use a single GPU. And for best performance, you best use only one MPI rank per GPU. If you have more MPI ranks than GPUs, then GPUs will be assigned to MPI ranks in a round-robin fashion. So I can briefly illustrate this. For instance, a 40 cubed 3D Poisson problem. I can solve this, let's say, using 4 OpenMP threads without GPU and without any compression. So this is low rank compression. So 40 cubed, so that means 64,000 unknowns, and this is the number of non-zeros. So because this is a 7-point stencil, this is about 7 times that. This is using a geometric nested dissection reordering. This is the number of frontal matrices, so the number of separators in the mesh. And this is the factorization time. We also see the time to do the nested dissection, time for symbolic factorization, and so on, the floating point performance. And then this is doing iterative refinement for the solution, but since it's an exact LU factorization, so we get the exact error in a single step of iterative refinement. And finally, the component-wise scaled residual is also quite good. So now we can try to enable GPU offloading. So now we get 275 gigaflop and 0.1 second. Compare this to 5 seconds. So that's a huge speed up. There is some, if you run this, you'll notice it takes a little longer than 0.1 second here. That there's some initialization cost of loading the CUDA libraries, which we don't time, but that's a cost you only pay once. When you run multiple solves and multiple factorizations, you only have this cost initially. And you see more output here. That's because the GPU algorithm traverses the tree level by level. And so we have some output for each level. And you can see the number of nodes in the supernodal tree on each level. So at the root of the tree, there's only one node. And the next level has 2 nodes, 4, and so on. And you can also see that the matrices get bigger as you approach the root, and the performance gets better as the matrices get bigger. So here we get 800 gigaflop per second. Okay, so now about the fill reducing ordering. The default is METIS, but we also have PARMETIS, which is which will only work in parallel. We have Scotch, PT Scotch, RCM. This is reverse Scott-Hill-McKee, which is not really a good fill reducing ordering, but it's there if you want to try it. And we also have a geometric nested dissection code, which only works for regular meshes like finite finite difference discretizations. But in this case, you have to specify the mesh dimensions. I'll come back to this. So you can still use METIS even though you're running the distributed memory solver, but then the matrix has to be gathered on a single process, the root process, which then calls METIS. So for very large problems, this could run out of memory, and the only thing you can do is PARMETIS. But typically, we notice that for the parallel ordering PARMETIS, the quality deteriorates if you increase the parallelism. And these methods also often stop scaling after a couple nodes, about like 100 nodes or so. So you can set these reordering methods using the command line option, or in the API, set the reordering method to Scotch, for instance. But then this will only work if you have configured STRUMPACK with Scotch support, which is optional. yeah, so sometimes maybe Scotch could have a lower fill or could run faster than Wheaties. So it's good to experiment with these. And I'm currently also working on adding a few more orderings, like minimum degree. And I'm working on a spectral nested dissection code too. And this will be added in a future release. And so for the geometric nested dissection, as I said, this only works on regular meshes. It could be 1D, 2D, or 3D. And so we have to specify the mesh dimensions. You can do that with set nx, the number of mesh points in the x dimension, y or z. For a 2D mesh, you only have to specify the first two, and then it's assumed that the last one is just 1. You can also do that on the command line. Or you can also have a regular mesh with a stencil which is wider than the standard 3 points per dimension. So 3 points are the point itself and its left or right neighbor. But if you have a wider stencil, you will need a wider separator too. So you can specify the separator with, or you could have multiple components per mesh point. You can also specify those. Then for the matching, which is used for column pivoting to get non-zero diagonal entries. So we have these options from the MC64 code, which has 5 different options. The default is to use option number 5. So you specify that using --sp matching. And option number 5 will compute a column permutation and also a row and a column scaling such that all the diagonal entries are 1 and all diagonal entries are less than 1. And then there's also support for combinatorial BLAS because this MC64 code is also only sequential, so that also needs to gather the entire matrix to the root and then call MC64. MC64 is typically quite fast, but this could become a memory bottleneck for large problems. So in that case, you can use the combinatorial BLAS. But that only works for now for powers of 2 processors. And you can also specify this with the API. So then I'll talk now about the preconditioners using rank structured approximation. First, I'll go over these rank structured approximations for dense linear systems. So the most general rank structured format is the H matrix representation, as illustrated here. So you can get to that by recursively partitioning the matrix in, say, 2 by 2 subblocks. And then you can look at each of the subblocks and decide, is this matrix compressible using low rank, yes or no? So you ask, is this matrix admissible, yes or no? If it is not admissible, so it's not low rank compressible, then you further subdivide it until you can compress it using low rank. So each of these low rank blocks is stored as a U times V transpose low rank product, and some other blocks you can keep them as dense. You can use this kind of matrix approximation to approximate all kinds of structured matrices. Once you have this compact representation, you can use it to do fast matrix vector multiplication, or you could compute a factorization of this, for instance, using an LU decomposition, which you can then use to compute an approximation to a linear system, or you can use this as a preconditioner. So I mentioned this admissibility condition, which is used to decide if a block can be approximated using low rank. And this is a condition typically based on the sizes and the distance between the 2 blocks in the physical domain corresponding to the rows and the columns of this subblock in the matrix. So for instance, you have a row cluster sigma corresponding to these rows in the matrix, and you have a column cluster tau corresponding to these columns in the matrix. So they correspond to physical points in physical space And if these clusters are close together, then that will lead to larger ranks in this subblock. If they are well separated, that will lead to lower ranks. So there's this condition called the admissibility condition to decide whether or not to compress this block. But to get good compressibility, it's important that you cluster your physical domain in order to find blocks that are of low rank. So one of the formats that we support in STRUMPACK is called the HODLR, or hierarchically off-diagonal low rank, which is a simplification of the more general H format, in that every off-diagonal block is now assumed to be low rank. So you partition recursively into 2x2 blocks, but you only further subdivide the diagonal blocks, and the off-diagonal blocks are approximated using low rank. This drastically simplifies implementation, parallelization, and also computing the inverse. But it can lead to larger ranks for these off-diagonal blocks, especially for say 3D problems or high-frequency problems. And then we have the HSS format, hierarchically semi-separable, which is somewhat similar to HODLR, but it has the additional property that now these low-rank basis matrices are nested. So a off-diagonal block is now approximated using a U times B times V product. So this U is a tall skinny matrix, B is a small, more or less square matrix, and V is also tall skinny, but then transposed. But we don't explicitly store U, but we store U as a linear combination of smaller U matrices. And these smaller are the low rank representations on a lower level. For instance, this U is this basis matrix, and this you multiply this with the lower level U matrices, so this one and this one, in order to get the low rank representation, this larger block. This reduces the complexity of the algorithm. It gets rid of an extra log factor compared to the simpler HODLR format. And you can think of this HSS also as a special case of the H square. So that's H, the more general format, with nested bases. So that's H square. Then in STRUMPACK, we also have support for block low rank, which is a non-hierarchical scheme where you partition the matrix in a grid of blocks, and you can compress each of these blocks using low rank, or based on some condition, you can decide not to compress certain blocks. Typically, the diagonal blocks are not compressed. You can say, let's not compress this block because we know from the geometry that it will not compress well. And then you can save some work, because suppose you try to compress this and then you find out that the rank is larger than, say, half of the block size, then it doesn't pay off to store it as low rank. So you will, it's more efficient to store it as a dense block. And then you can also compute, for instance, an LU factorization of this type of compressed matrix. So this is again an overview of the different formats. There's H, then HODLR, HSS, and BLR. So in STRUMPACK, we have support for HODLR, that's through Butterfly Pack, and we have HSS and BLR. So very briefly, these matrix representations are related to the fast multiple method and particle methods like Barnes-Hut. You can think of Barnes-Hut and FMM algebraically using H or H2 matrices. So Barnes-Hut would be an H matrix where these blocks are compressed using low rank, and in the fast multiple method, you also have this property of the nested basis where you express this low rank product in terms of the basis matrices at the lower level. And then there's the butterfly decomposition, which Jan Liu implemented in butterfly pack, and which we can also use inside STRUMPACK. And this is based on ideas from the fast the fast Fourier transform, and it's based on this idea of the complementary low rank property. So suppose you have this square matrix, and you can partition this in multiple ways in subblocks all of size order n. So this is an n by n matrix. You can partition this in blocks this way or this way, or then you can merge, say, two blocks and split them in this direction. You still have blocks of size order n. And now you assume that each of these blocks is compressible using constant low rank. This assumption then will lead to this multiplicative decomposition as illustrated here. So the square matrix of size n by n. So this is n rows and n columns here. And the product of all these factors, all these block sparse diagonal factors will give you one dense matrix. So you can think of this as a generalization of a low rank decomposition, which we then use within a hierarchically off diagonal format. So illustrated here is a hierarchical matrix, just like HODLR, hierarchically off diagonal low rank, but in HODLR we would approximate this off diagonal block using low rank. But now in HODBF we use a butterfly decomposition for this off diagonal block. So remember I said that the disadvantage advantage of HODLR is that these ranks of the off diagonal blocks can grow, but by using this more complicated decomposition, instead of low rank, we can keep these ranks much smaller. I'm going to skip that for the sake of time. So now we can combine these rank structured matrix representations with the approximate sparse multifrontal factorization. So that's just briefly illustrated here. So remember we have this separator tree or the supernodal tree. These dense blocks, for instance, this block corresponds to the root separator, which appears here at the bottom right of the reordered sparse matrix. So this is the sparse matrix reordered using nested dissection. So you can recognize this is one subtree, this is the other subtree, and this final block corresponds to the root separator, which is connected to the two subblocks by these elements here. And you do this ordering recursively. So this block here in blue is the root separator, which we will then compress. So the blue blocks here are the blocks that are compressed using a low rank. But since these blocks get smaller and smaller as you go down the tree here, there is a cutoff, and we only compress the higher levels in the tree because those correspond to larger matrices. If you do the compression on too small matrices, there will just be too much overhead. So that's an important tuning parameter, the size of the minimum size for a matrix to be compressed using these rank structured approximations. So you can set, for instance, the compression relative tolerance. Suppose you want to use a block low rank compression. So you can set the compression type to block low rank, and then set the compression relative tolerance, set the compression minimum separator size to, for instance, 1000. So that's exactly this cutoff level here. Only the blocks larger than 1000 by 1000 will then be compressed using low rank, and everything smaller than that is kept as dense. You can set the leaf size for the block low rank format. So you query the options structure, which inside has another options structure for DLR specific options. So there's another one for HADLR and HSS, for instance. So you can set the leaf size, which is the smallest block size. For instance, for a block low rank, it's the size of these blocks. They will not all be exactly 512 by 512 because these blocks are determined by doing a graph partitioning on the separator. But they will be approximately 512 by 512. We have also different versions of the block low rank factorization algorithm. We have left looking and right looking, and we have versions that reduce the peak memory, but it might be a little slower than other versions. And you can also set these from the command line if you pass the options. But because now the solver will be approximate, it's no longer computing the exact L and U factors. So we're using this LU factorization as a preconditioner. So you can set the outer Krylov solver, for instance, to preconditioned by CG-STAP or preconditioned GMRS. This is done automatically when you enable compression. If you don't enable compression, the outer solver is simple iterative refinement. But if you need more iterations, it's typically better to do a preconditioned Krylov solver than to use iterative refinement. So then we can combine different compression algorithms. So as I said, for the smaller matrices, we keep them as dense because there's too much overhead trying to compress those. The block low rank format, because it's not hierarchical, it's a little simpler than the other formats. So the asymptotic performance of the block low rank format is such that it works well for medium-sized problems, but for the very large blocks in the supernodal tree, we use this HODBF format, which uses the butterfly compression. So then we have this combination of formats where we use dense for the smallest blocks, block low rank for the medium-sized blocks, and hierarchically off-diagonal butterfly for the very largest blocks. So that's then this scheme, which I already showed in the beginning. I'll come back to that. But then we also have this ZFP compression, which is a lossy compression for floating point data, and we can also apply that to very small dense blocks. And that will then lead to a drastic memory reduction, even for numerically challenging problems. For very hard problems, you can use also lossless compression, but the compression rate there is not very good. The problem is that this lossy compression, we cannot do the triangular solves using the compressed matrix, so we have to decompress before we can do the triangular solve. But we can decompress block per block so that the peak memory usage is still reduced, but we do not save anything in terms of factorization time. We do save a lot in terms of memory usage. So the compression rate for this lossy compression is expressed in terms of bit planes. So if we compress using 8 bit planes here, we get a compression rate of say 8%. But then we need 20 GMRS iterations to recover the solution. So we can also combine this with block low rank and HODBF for these smaller levels. So that leads to the hybrid ZFP block low rank hierarchically off-diagonal low rank scheme. You can also use this to do the HODBF. There's a separate parameter to switch from low rank to butterfly. And these are the other compression types. In order to use HUDLR, you need to configure STRUMPACK using butterfly pack, and in order to use CFP or this lossy or lossless compression, you need to configure with CFP support. So here are some example results for viscoacoustic wave simulation or indefinite Maxwell simulation. So we scale this problem on a regular mesh. This is for the viscoacoustic wave equation. So I already showed this in the beginning of the tutorial, but now you should have a better understanding of what's going on. So we scale the problem from 150 cube to 500 cube. And the blue line is without any low rank compression. The green line is with the hybrid hierarchically off-diagonal butterfly plus block low rank compression. And so the orange line or the gold line is also including CFP. So note now that this costs a little more in terms of factorization time, because we have to additionally compress using CFP, which does not reduce the computation, the number of flops at all. It just adds extra cost for this compression. But it does significantly reduce the memory usage. Okay, so I think that's basically all I have for now. Maybe I can show in the hands-on also how to enable compression. So for instance, let's again run this Poisson example. Let's now disable GPU and run this without any compression. So as I said, it will then use iterative refinement, but since this problem is very well conditioned and it's an exact LU factorization, we get the solution in one step. So now we can enable block low rank compression. So now you see that the solver needs a few GMRS iterations to get the residual down. And here you can see the compression rate. So only 85% of the memory is required now to store the final LU factors. But you can see here that there are a total of over 6,000 dense frontal matrices, but only 3 block low rank matrices. That is because we're only compressing the top 3 block low rank matrices. And you can tweak this by setting, for instance, compression minimum separator size to, for instance, 256 instead of the default of 512. So now it's compressing the 15 largest block matrices as block low rank, and now we get a better compression rate, but still only need 2 iterations. You can also change the block low rank relative tolerance from 10 to the minus 4, which is the default, to say 10 to the minus 2. The compression is only slightly better, but now you need a lot more GMRS iterations. So there's this trade-off, right? Having a smaller compression tolerance will make the factorization faster, will reduce the memory here, but will make the solve slower. That's one benefit of an exact sparse solver, is that you spend maybe more time in the factorization, but the solve becomes faster. But you might run out of memory. So now we have this tolerance as a trade-off between time spent in the factorization and the solve, while also reducing the memory. other compressions are, for instance, the lossy scheme. Let me remove this. So for the lossy scheme, the threshold for compression is 8. So all matrices larger than 8 by 8 will be compressed. So we get a very good compression rate with that because we compress so many small matrices. So you can see that many more are now compressed with this lossy scheme, but still only needing 3 GMRS iterations. But the factorization time is now more because we cannot exploit the low rank arithmetic. Are there any questions?
So Peter, in the chat, I see at least one person, Renee, had a segmentation fault with testing one of the Poisson example.
Let me quickly try this.
Yeah, so I suggest that I have another person wants to talk to me about something else. So I'm going to my breakout room.
Okay.
Do people still have any general questions for me? I'm going to my breakout room soon.
I have a question about the convergence of iterative process in case of ill-conditioned problem. So apparently all these types of compressions, they do not preserve the kernel of the problem. Did you see convergence ruined by use of aggressive compression?
How do you mean by preserving the kernel?
Say you are solving the problem, Newman problem for Laplacian, right?
Yeah.
So if you have a preconditioner which preserves the kernel, right? Then the fact that your matrix is rank deficient is irrelevant for the convergence process. So you can still reach convergence even though the matrix is ill-conditioned. But no, not ill-conditioned, rank deficient in this case, deficient. Right? And all these compression techniques, they do care about fill-in only. They do not have a property of preserving the constant kernel, like the kernel of the Laplacian operator. So there's a risk that you will start polluting the kernel due to the fact that the preconditioner is approximate. So at the end of the day, you may end up with residual, which is irreducible, even with GMRS. Am I clear on the statement?
So I think first clarification is when we do this low rank approximation, we are compressing only the off diagonal block. So it's not the full, doing the full matrix of low rank approximation.
Yep. Yeah,
you mentioned the case that the whole matrix is rank deficient, right?
I don't think it makes sense whether you compress only the off diagonal or non, or include the diagonal blocks. The only important thing is that the preconditioner must have exactly the same kernel as the original operator. So all the modifications you do with the matrix, they're all legit and useful as long as the kernel is preserved. Once the kernel is polluted, then you may end up with residual, which is irreducible in iterative process.
Mm-hmm.
if you did observe something,
Yeah,
you know,
I don't think we, from my reading of the literature, I don't think we have that property, preserve the kernel. So there are some effort to preserve the positive definiteness. You
no, it is somewhat different, you know.
yeah, that's different, I understand, but there are some techniques to say at it's called maintain the Schur complement monoticity, which
I
means
see.
that which means that after each elimination step, your Schur complement is still positive definite.
Thank you.
Yeah, but that's very different. I think it's very different from what you.
Yeah,
Yeah.
and it may not be as kind of sensitive in case of, say, Laplacian, because it has just one-dimensional kernel. If you start considering more complex operators like, I don't know, div or curl, they have much larger kernel. It's not just one-dimensional. And I know in the special multigrid preconditioner designed for these operators, and they go into a lot of details, to preserve the kernel, because otherwise the process is not convergent. That's why I started asking this question. It's kind of,
yeah, that's very interesting. So I actually want to know more about this property. Do you mind if you send?
Yeah, we can talk offline if you want.
Yeah, we can talk offline. If you send us some references, so we should certainly take a look, and then we can communicate offline.
Sure. Thank you.
Yeah, that would be great to know what it is. All right, so I think I'm going to join my breakout room. Someone is waiting for me. Thank you all for attending. We'll see you throughout the week. And tomorrow we have posters as well.
Yeah, I'm still here. We still have 20 minutes if there are any other questions.
I'll go ahead and stop the recording.